Okay, in part B, we were on our way to finding out about enthalpy, but we're not quite there yet because first we had to go over the idea of internal energy. We're getting at internal energy, often the symbol is capital U or capital E, and there can be changes in the internal energy of a substance during chemical or physical processes. The internal energy of substance is essentially all of the various forms of energy within it, potential and kinetic together, totaled up. And so obviously, physical and chemical processes can produce changes in physical and chemical energy, and therefore they would also change the internal energy of the substance. If energy is transferred to or from the surroundings, the system will absorb heat from the surroundings. Absorbing heat from the surroundings would mean that Q is positive, and that would increase the internal energy of the system. Or in other words, delta U, that is change in internal energy, would be positive. But U can also increase if the surroundings do work on the system. That is, if the surroundings do work on the system, they're essentially adding energy to the system. That would be symbolized by W, and that would be positive if work is done on the system. That would be another way of increasing the internal energy of the system. A good example would be heating a metal wire. There are a couple of ways you can do it. You could heat the metal wire by holding it over a stove, in which case the wire absorbs heat, and that's kind of squeezed in there, but that would be an example of positive Q. So the heat flow is into the wire from the wire, or from the stove, I mean. Or you can also heat up a wire by bending it back and forth. If you've ever tried to basically cut a piece of wire without any wire cutters, and you just or you could try it with a paperclip, just try bending it back and forth until it breaks, and then feel it. The edges where it broke will be hot. Sometimes, actually, with some wires, they're pretty tough, and you can try to break it by bending it back and forth and back and forth and back and forth. And sometimes the wire will actually get too hot to touch. You have to put it down for a while and then come back to it because it gets so hot just from bending it back and forth. And that is an example of increasing the kinetic energy of the particles that make up the wire. You're doing work on the wire and you're moving the particles back and forth, and that friction of the particles as they move back and forth is what's causing the wire to heat up. But anyway, you're doing work on the wire, and that would be considered positive W. And so they both have the effect of heating up the wire. You could heat the wire up by doing either of those things, or you could do them both. You could heat it over a stove while bending it back and forth, and that would heat the wire up even more. All of these things would involve a positive change in U, the internal energy. And a positive change in U tends to correspond to an increase in temperature, because of course both of the things, as I said, are ways to heat up the wire. The internal energy of a system will decrease if the system loses heat, that is negative Q, or if it does work on the surroundings. If the system does work on the surroundings, then the system is giving up work, essentially, and that would be considered a negative W. Either of those will decrease the temperature and decrease the internal energy. If you have a situation where maybe Q is positive and W is negative, or the other way around, Q is negative and W is positive, then whether the internal energy of the system increases or decreases overall would depend on the relative magnitudes of Q and W. So it would be when you add the two together that you get the change in internal energy. So if you want to look at the relationship between heat and work, we can look at just the change in internal energy of a system during any process is just equal to the total of heat and work, or Q plus W. And the relative signs of Q plus W and their relative magnitudes will determine whether delta U is positive or negative. Okay. This is known as the first law of thermodynamics. That is, the internal energy of a system can change through either heat flow or work, or both. So there are essentially two components to the internal energy of something. So just as a bit of a review of what I was just saying, for Q, that is heat flow, positive Q would mean that heat flows into the system, or in other words, the system gains heat from the surroundings. And negative Q would mean the heat flows out of the system, or in other words, the system releases heat to the surroundings. W, that is work, if W is positive, that means work is being done on the system by the surroundings, and the system gains internal energy. Negative work would mean that the work is being done by the system on the surroundings. So the system would be losing work or losing energy in that case. And as I said, it's the balance of the heat versus work that determines whether the system gains energy, which would be a positive delta U, or loses energy, which would be a negative delta U overall. Now, of course, you can probably guess that in the case of chemical reactions, work is usually not a very significant factor, unless there's one exception, unless gases are involved. The one time that work in a chemical reaction will be significant is if the reaction involves gases. Because if you generate gases in the reaction, those gases will need to expand, and because gases, like I said, take up a lot more space than solids or liquids or aqueous solutions. Generating a gas causes the gas to try to expand, but there are already gases out there. So if you're generating a gas in a reaction, it's going to have to expand against the pressure of the gases that are already out there in the atmosphere. And that will be your system doing work on the surroundings, because it takes work to expand a gas. On the other hand, if the reaction uses up moles of gas, or maybe it uses up moles of gas but it doesn't produce enough moles of gas to replace them, so there's a net decrease in the number of moles of gas, then the system compresses. It takes up less space than it did originally, and that would be a case of the surroundings doing work on the system. The system actually gains energy if it contracts, because the outside gases are pushing on the system, and that does work on the system. So this is known as PV work, or pressure volume work, because changing the volume of a gas against an outside pressure is an example of work. So PV, pressure volume. Okay, sometimes also called expansion work. Okay, so again, producing a new gas pushes out against the atmosphere, and that's the system doing work on the surroundings. So producing a new gas is negative work. The system loses energy. Consuming a gas or producing less gas than you use is positive work, because the surroundings do work on the system. So in other words, if the number of moles of gas in the reactants is greater than the moles of gas in the products, that is, you've used up gas overall, then PV work on the system is positive, and that means delta U would tend to be positive. And if the number of moles of gas in the reactants is less than the moles of gas in the products, in other words, if you're producing more gas than you're using up, then you have to expand that gas against the atmosphere, and that's the system doing work on the surroundings. So the PV work would be negative in that case, and that would tend to make delta U negative. And if you want to calculate the actual PV work, it's going to be equal to P times delta V. That is pressure times the change in volume. And the reason that it's pressure times change in volume rather than, say, change in pressure times change in volume is that most chemical reactions are done open to the air, in an open beaker or in a calorimeter that doesn't have an airtight lid, that kind of thing. So the pressure normally remains the same, and it's the volume of the gas that expands against the gases that are already there. So in most cases, it's the volume that's actually changing. The pressure usually remains constant. So you just take the value of the pressure times the change in the volume, and you've got the value for the PV work. A good example of that is burning a fossil fuel in an internal combustion engine, like say gasoline. Gasoline is a mixture of several different compounds consisting mostly of carbon and hydrogen. Some of them also have oxygen in them. And generally the carbon becomes carbon dioxide and the oxygen becomes water vapor, and any oxygen in any of the compounds will come out as part of the carbon dioxide or the water vapor. It can go either way. And combustion releases energy as heat. So heat is one of the products. And certainly, your engine requires an entire cooling system of water flowing through the engine and then going through a radiator to cool back down again and then going through the engine again. Because otherwise, this reaction of combusting gasoline in the engine produces so much heat that it could actually cause the engine to melt. The steel or iron or aluminum parts in the engine would actually melt from there being so much heat involved. And so it definitely generates a lot of heat. And it also does work, because burning of gasoline creates a lot more gaseous products than it uses in gaseous reactants. And so the overall expansion of those gases against the pressure of the gases already present is actually what causes the piston in the engine to move downward. When the piston is at the top of its travel, the piston is just this sort of plunger-like thing that moves up and down within the cylinder. And when it's near the top of its travel, the fuel injection system injects a little bit of the sort of a gaseous spray of gasoline mixed with oxygen from the air. And the spark plug at that moment ignites, and that causes the reaction to occur all at once. And the reaction produces a lot of carbon dioxide and a lot of water vapor, in excess of the moles of oxygen used. And the expansion of those gases is what pushes the piston back down again. And that reaction occurs many times every second in all of the different cylinders in the engine. So what you get is that constant cycling of pistons going up, pistons going down, pistons going up, pistons going down. And that motion is used to turn a crankshaft, which is connected to your transmission, which is connected to the differential, which moves the wheels. And that's what actually makes the car go. As a representative of the compounds in gasoline, we can use iso-octane, which is one of the compounds in gasoline. It's added to increase the octane rating of the gasoline, which makes it less likely to knock in the engine. And so that is one of the components in gasoline. We can show this a balanced equation wherein for every 2 moles of octane that are burned in the engine, 25 moles of oxygen are used from the air, but 16 moles of carbon dioxide and 18 moles of water vapor are produced. That's all gases. So you've used up 25 moles of gases, but you've generated 34 moles of gases. So that's a net gain of 9 moles of gases every time this reaction occurs. So that's a lot of excess gas being produced, and that's why it's able to do so much pressure volume work in addition to the heat that's released. Okay, internal energy is a state function. And remember what we mean by state function. I think we've mentioned it before. Anyway, if we haven't, then state function is the kind of thing that only depends on where you start and where you finished. Doesn't matter how you got there. Kind of like delta T. Delta T, change in temperature, is a state function. It only depends on what the initial temperature was and what the final temperature was. Doesn't depend on how you get from one place to the other. And a good example of that is kind of like also the change in potential energy as you climb a mountain. Potential energy is just your weight times your height above the surface of the earth, generally measured from sea level. So if you're climbing a mountain, your height above sea level is changing. And your change in potential energy is really just going to depend on how high you end up versus how high you started. And it doesn't matter whether you go straight from the base of the mountain to the top or whether you take a circuitous roundabout route from the base to the top. Your change in potential energy would just be your potential energy up here versus your potential energy down there. And again, it's just the difference between the initial and final points. It doesn't matter how you got from one place to another. Distance, on the other hand, is not a state function. It does depend on what route you take. Obviously, the roundabout route will be a much longer distance than the straight route. But again, change in potential energy will be the same either way. And so internal energy is that kind of situation where it only depends on where you start and where you end up. Another way of thinking of that is that delta U, that is changes in potential energy, means the net change in internal energy. Just like delta T means the net change in temperature from the initial to the final temperatures. Okay, so it depends only on where you start and where you end up. Doesn't depend on how you get from one place to the other. Heat and work, on the other hand, are not state functions. They do depend on how you get from the initial to the final state, but internal energy does not depend on that. This brings us finally to enthalpy. Enthalpy is related to internal energy, and we'll get to that in a moment, but it's more commonly used than internal energy because it's easier to measure. It's related to internal energy, but it's not exactly the same thing. And enthalpy is just the total of the system's internal energy plus any pressure volume work done on or by the system. So enthalpy is equal to internal energy plus PV. That actually is also relatively difficult to measure. What's a lot easier to measure is changes in enthalpy during the course of a chemical reaction. And in fact, we care more about that anyway. We care more about how enthalpy changes than what its absolute value is at any given point. So the change in enthalpy, or delta H, for any given reaction will be the change in internal energy, or delta U, plus P times delta V, pressure times change in volume. And again, we don't use delta P because that normally doesn't change during a reaction. And remember, P delta V is equal to negative work. So looking at what the above actually means, delta H equals delta U plus P delta V, substituting in what these things are equal to, we already saw before that delta U is Q plus W. In this case, I'm putting a little P after the Q just to indicate that this is done at constant pressure. The pressure is not changing. But anyway, delta U is Q plus W. And P delta V is negative W. So Q plus W minus W is Q. So as long as the pressure remains constant, delta H is equal to Q. Okay? And so that's why I circled that. That's important. Delta H is the same as Q as long as the pressure remains constant. So if the reaction is done at constant pressure, in other words, the pressure doesn't change during the reaction, and the only work done is due to expansion or compression of gases, then the enthalpy change is the same as the heat flow, Q. But that means that the reaction has to be done in an open container if any gases are involved. Otherwise, the pressure would change. So in other words, delta H is not equal to Q in a bomb calorimeter, because in a bomb calorimeter, the pressure does change. Unless you're doing a reaction that doesn't involve any gases, but it would be unusual to do something like that in a bomb calorimeter, although you could. So when using delta H, remember a few things. Delta H is also measured from the point of view of the system, which in chemical terms usually just means the molecules of the reactants, nothing else. The water is part of the surroundings. The products are part of the surroundings. The thermometer is part of the surroundings. The system is just the molecules of the reactants. And a negative delta H, in other words, delta H is less than 0, means the reaction is exothermic. In other words, exothermic would mean the temperature goes up. So actually, delta H and delta T normally have different signs. So if delta H is negative, delta T is positive, because remember, the thermometer is measuring the temperature of the water, and the water is part of the surroundings. So if the temperature of the water goes up, that means the system has lost energy. So that would be a negative delta H. Positive delta H, in other words, delta H that's greater than 0, means the reaction is endothermic. But it also means that the temperature has gone down. So positive delta H means negative delta T. The temperature, again, is measuring the temperature of the water, which is part of the surroundings. So if the surroundings lose energy, the temperature goes down. That means the system must be gaining energy. So delta H is positive. If a reaction is reversed, delta H remains the same in magnitude, but the sign changes. So that just means if you do a reaction forward and you get out a certain amount of energy, if you want to do that reaction backwards, then you have to put in that same amount of energy. So it's the same amount of energy either way, it's just whether you're getting it out versus putting it in. And the difference there would be, mathematically speaking, the sign, positive or negative. In using enthalpy, we often involve what are known as thermochemical equations. These are chemical equations. Thermochemical equation is a chemical equation balanced to use or produce 1 mole of whatever substance is of interest. It could be a reactant or it could be a product. And it's also accompanied by a statement of the delta H for this reaction, as it's written, would be so many joules or so many kilojoules, positive or negative, depending on whether it absorbs heat or releases heat. So for example, the thermochemical equation for the formation of water from its elements, for that reaction, we would normally write 2H2 plus O2 yields 2H2O. But for a thermochemical equation, say if we're interested in the formation of water, we're going to want it to form 1 mole of water, which means that all of the coefficients have to be divided by 2. Little catch though, the coefficient for oxygen is 1. And when you divide that by 2, you get 1/2, which is a fraction. And that means that actually in thermochemical equations, fractional coefficients are allowed. We normally don't like fractions, but they are allowed for thermochemical equations, because here the important thing is getting 1 mole of the product or the reactant, whichever you're interested in. So the thermochemical equation for forming water from its elements would be H2 plus 1/2 O2 yields H2O. Now, of course, in practice, if you're to do this at the molecular level, you can take 1 molecule of hydrogen. You can't find 1/2 molecule of oxygen, because that would just be an oxygen atom, and they don't normally exist in nature. But we don't normally look at these at the molecular level anymore anyway. We usually think of these in terms of moles, and you could certainly have 1/2 a mole of oxygen. That's what that means. 1 mole of hydrogen and 1/2 a mole of oxygen yields 1 mole of H2O. Notice also that the thermochemical equations, it matters what the states of the substances are. Hydrogen is normally a gas, and oxygen is normally a gas. Water could also be a liquid, or it could be water vapor. In this case, it's hydrogen gas and oxygen gas are producing H2O liquid. And delta H for this reaction, as it's written, would be negative 286 kilojoules. That means the reaction as it's written gives off 286 kilojoules of energy. Since this is written to produce 1 mole of H2O, we could also think of delta H as negative 286 kilojoules per mole of H2O. Okay, so you can think of that either way. So like I said, fractional coefficients are allowed because you basically want 1 mole of the reactant or the product, whichever you're interested in. And that if that takes fractional coefficients to make it happen, then so be it. If the thermochemical equation coefficients are multiplied by a factor, then delta H also needs to be multiplied by that factor. So like in this case, if producing 1 mole of water releases 286 kilojoules, then producing 2 moles of water should release twice as much, right? Makes sense. And so that's what that means. And that's because delta H is an extensive property. It depends on how much stuff you have. So if you write the reaction the way we normally do it, 2H2 plus O2 yields 2H2O liquid. Delta H would be 2 times negative 286 kilojoules, which is negative 572 kilojoules. And also the enthalpy change depends on the physical state of reactants and products. Above here, I had hydrogen gas and oxygen gas yielding water in form of liquid, the way it's normally found at normal temperatures. But you could also write it as hydrogen gas plus oxygen gas yields H2O gas, water vapor in other words. But that has a different delta H. So when you're consulting the tables of tabulated values for things like delta H's, you have to be very careful about looking at the phase label, making sure that you're getting the right form of the substance as well as the right substance. Because negative 242 kilojoules is quite a bit less than negative 286. I mean, it's quite a bit less energy that's being given out. Okay, so just a quick example before the end here. If you have zinc reacting with hydrochloric acid, so 1.34 grams of zinc solid reacting with 60 milliliters of 0.750 molar hydrochloric acid, 3.14 kilojoules of energy is released. What is the enthalpy change per mole of zinc? All right, so you might think, okay, we just take the kilojoules divided by however many moles of zinc are in 1.34 grams, and we got it. Well, actually, the first thing you have to do is make sure what the limiting reagent is, because they gave you a specific amount of both zinc and hydrochloric acid. So you need to know what the reaction is. So this is a single displacement reaction of zinc metal with an acid. So it's zinc solid plus 2 hydrochloric acid moles yields ZnCl2 aqueous plus H2 gas. This is our reaction. We need to find out whether there's a limiting reagent here and which element or which reactant is the limiting reagent. So if we start with 1.34 grams of zinc and there's 1 mole of zinc for every 65.4 grams of zinc, notice the units cancel out, and there's 1 mole of zinc chloride product per mole of zinc, that means we have enough zinc to produce 0.0205 moles of zinc chloride. But if the HCl runs out first, that would mean that not all of the zinc reacts. And we would want the delta H for this reaction in terms of kilojoules released per mole of zinc that actually reacted. So we got to make sure that zinc is the limiting reagent. If zinc is the limiting reagent, that means it all reacts, and we can use the amount given in the problem when we find out delta H in kilojoules per mole of zinc. If the HCl turns out to be the limiting reagent, Then we would have to find out how many moles of zinc actually react with the number of moles of HCl and use that to find kilojoules per mole of zinc. But anyway, for the hydrochloric acid, you've got 60 milliliters, which is 0.060 liters at 0.750 moles per liter. So that will tell you how many moles of HCl you have. And the reaction tells you that you get 1 mole of ZnCl2 for every 2 moles of HCl. And so when you work that out, you have enough HCl to produce 0.0225 moles of zinc chloride. So fortunately, zinc was the limiting reagent. You end up with a little HCl left over. And so that means all of the zinc reacts. So you can use the amount given in the reaction to find kilojoules per mole. For delta H would be negative 3.14. It says that 3.14 kilojoules is released. That means for delta H, it's negative 3.14 kilojoules over the number of moles of zinc, which is just 1.34 divided by 65.4, which is 0.0205. And that would be negative 153 kilojoules per mole of zinc. So that would be your final answer, finally. Okay, so it wasn't such a quick example. Anyway, that gives us less to do next time, I guess. We'll pick up here next time in the lecture. This is the end of part C for today. And next time, just as a preview, we'll do some more examples similar to this one with delta H per kilojoules per mole, that kind of thing. Okay, so we'll pick up there next time.